Hi everyone, and welcome to the motor unit and nerve conduction component of your nervous system section. We will first discuss the motor unit, what it is, how it works, and then we'll dive into nerve conduction and how that works. First up, we can look at our motor unit. The overall function is to cue up motor activity. As we know, skeletal muscle is under direct neurological control, and because of that, we have special neurons that are designed to do that. When we have what's called an alpha motor unit, that is, again, involved in having us move through our skeletal system. So it's a specialized nerve. It has a special design, and the idea is that it has lots of short dendrites close to the cell body and a long axon that will reach out to the muscles that we're trying to get to move far away from the cell body, which is usually closer to the central nervous system. So here we have a couple of basic motor units, motor neurons, and again, some grouping of them. We can see we have two motor neurons here, and they innervate different muscle cells. And each motor unit will have a different number of innervations with a different number of muscle fibers, depending on what sort of function it is primarily involved in. And we'll get to that a little bit later in this lecture. But again, here are the dendrites close to the cell body, long axon that reaches out to the muscle fibers. When we have nerve conductions, and I think actually, this is getting a little far ahead. Keeping this in mind here, even before we jump ahead, we're going to learn how a signal gets sent all the way down a neuron or an action potential, because we want a signal to get from here out to here and conduct it down to there. And there's this idea of a all or none principle, where a signal that starts and reaches a certain point here, the axon hillock, and gets sent down the axon will excite and cause everything down the axon to have a signal sent down it. Okay, so that's an action potential. Now, to give you a bit of a background before we get into this, it's good to visualize in your mind a banana standing or floating in the ocean. Okay, so nerves or neurons, as far as their electrolytes are concerned, inside of them are much like a banana. So they have potassium in there. Outside of these neurons and just within our interstitial fluids, so fluids around our cells, are slightly selenic, which means they have some sodium in them, or and much like the ocean, it also has sodium or salt in it. So that's where this image of a banana in the ocean will come from. Now, why does that matter? Well, it is exclusively the exchange of those two ions, sodium or salt and potassium, between either side of a neuron's cell membrane that allows an electrical signal to be conducted, or a action potential, as we call it, be sent down as a signal through the cell. When we're at rest, here's our potassium inside of the cell, our sodium outside, and we see the interior is negative, exterior is positive. And we'll have two events occur primarily that you'll want to know. One is depolarization, which is as we get a signal or an actual potential occurring, we'll have a bunch of sodium flow in through this, what is called a voltage-gated ligand channel, which sits in the cell membrane. They'll fly in. These will enter the cell because of the electrical gradient that sits here on the cell membrane. And then we want to reset or repolarize the cell so it can send another signal. And to do that, the potassium channels open, and what generally has potassium from within the nerve cell, so our banana, flows outward, and we go through a process of repolarization. So what does that electrical signal look like? Again, don't worry about this part quite yet. But if we just look at the graph here, we can see we have a membrane potential in millivolts, and volts, as you can imagine, are electrically related. And then time in our milliseconds down here. So you can see within 1 to 2 milliseconds, our nerves have fired and are reset, ready to go again. Very fast. So we have this resting membrane potential, which sits along this bottom dotted line. And as you can see, that's roughly at about 68, 68 millivolts. Then what will happen is we get the stimuli to depolarize. And as that occurs, if we get enough of that signal from the dendrites and the cell body to undergo depolarization, we say that we've reached threshold. So when the cell has reached threshold, we get a all or none signal that gets sent down the axon. And as that happens, as noted on the last graph, we have our influx of sodium into the cell, and that's where we see this change from a negative resting membrane potential up to a positive, roughly 40 millivolt membrane electrical gradient, which will then start undergoing our repolarization phase. So this is where the potassium ions start flooding outward of the cell and help reestablish and actually overestablish the resting membrane potential, which will, over the matter of a millisecond or so, slowly rebalance out to be at this resting membrane potential. So we get that rebalancing of sodium and potassium ions after the sodium gate closes. Okay, right here at number 8. Sorry. So hyperpolarization is this phase here. Repolarization is this phase. This is resting membrane potentials. Depolarization, once threshold has occurred, then we get an action potential, which is our signal. Okay, so kind of looking at these together, just if you want to view this again, right? Depolarization we said was here. Sodium ions fly in. Re and hyperpolarization occurring there. This is when our potassium channels are open. Okay, so an overview again, our action potential is that electrical stimuli that causes a muscle fiber to contract. Threshold must be met, and our resting membrane potential means no impulse is being conducted. It just sits at this gradient held in balance by our ion concentration across the nerve cell membrane. Inside we have our negative resting membrane potential. Outside is positive. Our distribution of charges between the inside and outside of the neuron, with that change or depolarization or leading to depolarization, allows that threshold to get hit. So that's when our sodium gates open and it enters the cell, and then when we get to repolarization, the potassium channels open. Okay, so we need to explore how and why these signals transmit at different speeds. One of the main reasons that some nerves will conduct much quicker than others is because of this idea called myelin sheath. Okay, so it's nothing to do with the amount of electricity that goes through a depolarization. Remember, this term all or none occurs when we get depolarization, and it's always at set amounts of millivoltage. What changes for the speed or how quick we get nerve signals sent is the role of myelin. Now, a myelin sheath is a white, fatty, or lipid sheath that wraps around an axon. And so we have these myelinated nerves that are kind of like wires wrapped in plastic wrapping in a certain sense. And what they do is they allow for something called saltatory conduction, which we'll chat about in a moment. And that essentially utilizes these things called nodes of Ranvier, which are these little gaps in between the myelin sheath that allow the signal to jump along. Okay, so a good example of nodes of Ranvier that I use is from the second Lord of the Rings movie, if you've ever seen it. What happens in this is there's a bunch of stacks of wood piles of wood at a bunch of mountaintops across this huge, expansive mountain range, and they're trying to get a signal across hundreds and hundreds of miles, thousands of miles, very quickly. So how do they do this? Well, they send a signal from one mountaintop to the other by lighting these fires. So the fire gets lit at the top of one mountain on the stack of wood, and then the person way, 100 miles away or 100 kilometers away can see this flame, or even 50, and so they light a flame. And then the next person lights a flame. And so we get this signal that skips along. Whereas if they didn't have this system set up, they'd have to walk all the way up a mountain, down a mountain, up a mountain, down a mountain, and so on and so forth for hundreds and hundreds and thousands of miles. It's a very slow signal to deliver a message that way. This is exactly what the nodes of Ranvier help do. They increase the velocity of our neural conduction, and it also conserves energy in this process. So how does that look? Well, here we have our unmyelinated axon or nerve cell here, and we can see this local action potential propagating down the cell body. We see our influx of sodium, and then outflux of potassium, which allows this active signal to be conducted down. But when we have this myelin sheath, or this wrapping all the way around the axon, what happens is these loops at which this occurs is much greater. So you can think of the signal hopping along to each of these little nodes rather than having to go along every step of the way. And that is the great effectiveness of our nodes of Ranvier and myelin sheaths. Okay. So we understand now that we have this all or none signal of a nerve cell. We understand that the way that we can make signals go quicker is by using nodes of Ranvier versus just local signaling and depolarization. How do we get larger or smaller force production muscles? Okay, we recall back to this motor unit. So some alpha motor neurons are able to innervate a few muscles fibers, some do hundreds. But if we just activate one motor unit through this all or none principle of a single signal getting sent down, one of these neurons recruiting all these fires, how do we get all of the muscle to fire sometimes, or some, or every third, or how do we get a graded rather than this huge contraction or no contraction to occur? Well, the idea is kind of twofold. It's the size principle and the motor unit recruitment patterns that we do. So the size principle says that the motor units that are recruited, we go from our smaller motor unit. So for example, a 1-to-1 motor unit to muscle fiber. Again, smaller number just as an example, to larger. So from one motor neuron going out to 100 different muscle fibers. And that's generally how it works. The exception to this is when we need a large amount of force generated quickly. In these cases, high threshold, so normally neurons that take a lot of spurring on before they depolarize or reach threshold, so these high threshold fast motor units, they're recruited first in these instances. But again, that's when time delay is not useful to generating large force. And again, we'll look at that in just a moment. And again, with these all or none laws, what will happen is we will get more and more motor units recruited over time. And that allows us to turn off and on different muscle fibers and different motor neurons to occur to add up or summate to get the amount of force that we actually want. So we get this graded increase of force over time depending on how we're recruiting our motor neurons. And I like this graph because it will show you recruitment threshold of the different muscle fiber types. So we're looking at type 1 and type 2. and how much force production we're expecting. So initially, at a low threshold, at a low force production, we see all our type 1 muscle fibers getting recruited, okay? But as we need more and more force, we have to recruit these higher and higher level threshold muscle fibers, primarily type 2. Now, the exception being, even though it says power here and high force strength here, being that in a quick instant, sometimes rather than going through this path of lower to greater size of motor units, what we'll also see is a skip to here in the power and high force strength type things, where we're doing 1 to 5 rep maximum efforts or needing to do so with speed. We will skip the cue, so to speak, and immediately recruit these high threshold, high force production motor units. Okay. All right. And that was motor units and conduction of impulses.